All right, thank you. Happy to be here, and thanks BNP for having me, and whoever on the organizing committee had the idea to invite me. Very happy to be here. It's my first BNP, and yeah, actually, I think maybe Miss Chagas, this is not it's not particularly technical talk. I think it's a step down from most of the talks that I've seen here in terms of the mathematical sophistication. It's mostly just an opportunity to talk about things that I like to talk about, which is Bayesian nonparametrics and causal inference, and why I kind of like taking Bayesian nonparametric approaches to causal inference problems. Before starting, just acknowledge some collaborators. So Qing Zhang from Florida State, a former colleague, and then some grad students. So Angela Ting, who just graduated from UT, Prabita Kundu, who just graduated from UC Davis under Hans Georg Mueller, and Integer, who is possibly here. Yes, there he is. Hopefully we'll graduate someday. Uh, he's doing very good. Okay, yeah. So the main point is if you take away nothing else from this talk, the main thing I want to convey is that I think if you properly use Bayesian machine learning, if you do things sort of correctly, I find these methods to be sort of uniquely suitable for learning heterogeneous treatment effects in causal inference problems. And I'll talk a little bit more about what specifically that means. And specifically as well, there's lots of interest in estimating heterogeneous treatment effects right now in a lot of different disciplines. But sort of specifically, I find Bayesian thinking to be very helpful for kind of framing the estimation problems and certain things that end up happening when you try to estimate heterogeneous treatment effects. Just a little bit of notation before we jump into things. So this is all standard causal inference stuff, although if you haven't seen it before, it might be potentially new. But we're interested in some outcome. So outcome y of a. So a is taking one of two values in this particular setup. We'll say a is 0 if you are, this basically corresponds to control or to the placebo. 1 for the treatment, and then yi of 1, for example, is the outcome that you would have experienced had you been treated, and yi 0 is what you would have experienced if you had received the control. And you can write that sort of generally as a, so x in this case is going to be some set of either confounders or effect modifiers. So confounders are things that are maybe in a non-randomized setting. Those would be things that are confounded with the treatment assignment that you need to control for, or in the case of HTEs, you're interested in how are the covariates modifying the effect of the treatment itself. So we have an overall prognostic effect of the covariates. So that's what mu of x is. And then the object of interest for us is going to be tau of x. That is the treatment effect function. So I want to learn summaries in some sense of this function tau of x. So either I want to estimate the whole curve, or maybe I want to estimate some particular summaries of that function. In order to make progress in causal inference, you require some assumptions to kind of have a well-specified statistical problem. And I list them as axiom, right? I mean, they're all subject to critique, and in particular, this ignorability assumption, which basically says that your collection of covariates, so your x, is strong enough or sufficient to make the treatment assignment A, so this is the treatment that you receive, independent of your potential outcomes. So this is basically that I've measured all of the confounders of the treatment assignment and the potential outcomes have been measured and are controlled for. So that's a strong assumption, but we'll just take it as given for the purposes of this talk. The other ones you need to, as you say, that you basically observe the potential outcome at the observed value of the treatment. And the last one, overlap, just says that everyone has some chance of receiving one of the treatments. So there's nobody who is always a control or is always a treatment, right? And in any of these cases, you would not be able to identify the effects. So I'm talking about heterogeneous treatments. So that is, how does the treatment effect of the treatment vary throughout the population, and sort of why would you want to have be interested in treatment effect heterogeneity? So there's two settings, right? You could be in an RCT, so maybe I am randomizing people to treatment, and there maybe I want to identify subgroups of the population that respond better to treatment than other subgroups of the population. So I want to find, you know, in the most extreme case, maybe the treatment hurts some people and it helps other people, and I would like to identify who it hurts and who it helps. Or maybe I want to prioritize people, like I want to assign the treatment to the people that will benefit the most, and so forth. So that's an RCT sort of motivation. And then observational studies are much more complicated because in an RCT, you know that ignorability holds because you control the randomization mechanism. But in observational studies, you don't. And there's always this issue of the feasibility of the ignorability assumption. But at a very high level, you might be interested in treatment effect heterogeneity because if you identify very, very large effects, it's somehow harder to explain it away by confounding. If you identify an effect that is apparently large, it's a little bit harder to explain it away purely by confounding with the covariates. So if you can identify populations where the effect seems to be large, that would be potentially lead you to a more robust inference. And there's lots of recent work on machine learning and heterogeneous treatment effects, and especially in the econometrics literature. It's like really taken off there recently. And I just list one of the algorithms. So this is something that I think is like a dyed-in-the-wool Bayesian would be almost never led to do by training, but is a very popular thing to do and has lots of nice properties. You see lots of methods based on data splitting. So this is one possibility. You split the data. You then estimate two nuisance functions. So you estimate the regression function of y. So you regress y on x. So y, my outcome, my covariates. I get some marginal regression of y on x. I get a propensity score for the probability of treatment. I regress the treatment of A on X on half the data. And then on the other half of the data, you form these residuals and you regress them on each other. And you can, so if you sort of think about it sufficiently hard, you see that this is like actually a pretty reasonable estimator of tau X. After doing this generally to account for this, you then flip the roles of the data and average to get a final estimate. And then nice thing about this is like tends to have very nice sort of frequentist properties. Now, the one thing like I've sensed from Bayesian folks is that there's a fondness for betting. And one of the things that you can bet on if you would like is whether Susan Athey will win the Nobel Prize before 2030. Who is sort of credited with introducing many of these methods to, or machine learning more broadly to estimating heterogeneous treatment effects in the econometrics literature. So yeah, very, very popular, these sort of arms of techniques. One of the claims I'll make is that even by frequentist standards, it seems to me like Bayesian nonparametric methods perform well for inferring these things. So there's make a couple of claims, but this is one of them, is that even if you're frequentist, you're often well served by using Bayesian nonparametric methods. So the method that has kind of taken hold in the causal inference literature that's like actually picked up steam outside the Bayesian community is the BART model. So people outside of, say, BNP are well aware of this model if they're doing causal inference. You model outcome as a sum of decision trees. So y is decision tree 1 plus decision tree 2 plus so forth. You model the error with a normal, and you model each of these little decision trees. You add them up. You put priors on everything, and then you sort of do MCMC to get inference. This method, like it seems to actually work in a lot of cases. I'll give some sort of some kind of takes on it. Sometimes what you'll see are papers will put out these sorts of benchmarks that people look at. This is one from one of my papers. But yeah, generally, if you do these sorts of things, or at least if you look in the BART literature, often you'll find one of these tables where they compare root mean squared error and so forth, and Seems to do well. I regard it as weak because, it's not that many data sets here, although there is like a consistent trend on these sorts of data sets that you pull offline that it does seem to really work well relative to the standards that other people will do. So honestly tuned boosting or random forest or so forth empirically don't seem to perform well. At least when I tried to do it, I'm not able to get quite the same performance. I'll quickly pitch my own work. Won't hover here, but I have this is from a paper where I introduce a method called soft BART that has some nice properties. It's just a BART where you sort of smooth things. So instead of getting a step function-y looking thing, you get a kind of a curvy thing instead. But yeah, so that's regarded as like sort of like weak evidence that maybe these things would be useful for estimating nuisance parameters in these types of problems. Somewhat better evidence, I think, are these more controlled competitions that people have run. So ACIC, or Atlantic Causal Inference Conference, has held annual competitions, basically saying, like, we're going to set up some simulation experiment. It's hard to validate these things. In practice, how do you know whether one method is going to work better than another method? Because like not like in predictive problems, of course, you can just compare like which one is predicting better. In causal inference, you need to know the ground truth to really actually make a determination on it. And you never have that with real data, at least outside of very sort of narrow situations. So what a subset of the community is sort of centered on is creating, benchmark data sets that are designed to mimic features that we think are present in real data. And everyone is then invited to submit their method. So there's all kinds of communities that participate in this. There's the Bayesian nonparametric BART people, but there's a community of people who do things like targeted maximum likelihood estimation or de-biased machine learning and all these sorts of things, causal random forests, and just have them all compete. And a trend over the years has been that methods based on BART just sort of seem to work empirically quite well. So this is one competition. They do this they do this year over year. It's from Dory and others, and I think this is in statistical science. You see, right, like so, and this is just bias RMSE, and this is all for ATEs. But most of the, I think, 1, 2, 3, 4, 5 top performing in terms of bias and RMSE on this particular thing were using BART in some way. And then in coverage, kind of a similar story where the best performing methods were sort of seeming to somehow use BART and getting the best performance. Now this is just 1 year, so there's you might worry like, okay, well, who designed this particular thing? It was just like some guys. 1 year it was run by Mathematica, and presumably Mathematica doesn't have it in the tank for BART. And then in this particular year, for estimating subgroup conditional average treatment effects, we had 1, 2, 3, 4, 5, 6, 7 or so of the top performing methods all using BART. Yeah, I regard this as like reasonably strong evidence that these methods seem to work for whatever reason. Now, maybe you don't believe in the simulation experiments, that's fine, but there is some, I think, compelling theory that gives you some reason to believe that possibly these, you should expect good performance from Bayesian nonparametrics and BART in particular. The BART models are very adaptive, meaning that the function can satisfy all kinds of constraints. So like it could be additive, or it could have, it could be anisotropic in various ways. And you can show these results that basically say, like, okay, we're kind of regardless of what the structure is, you can get the minimax rate up to some log term. So this is one result from the soft BART paper, but Veronika Rychkova has worked on many other, basically shown adaptation to many other classes, interesting classes of functions. So as a method, it seems to be very adaptive, and it's like I sort of view this as speculative. I don't know how seriously to take these kind of convergence rate arguments for why these things work in practice, but there is at least some compelling theoretical story for why you should expect these things to work well, which I find kind of interesting. Yeah, so point is like even by frequentist standards, I think these methods are quite useful. But now I'll get into more sort of like why we might want to lean into being kind of being Bayesian as opposed to, judging these things in frequentist terms, is that often these heterogeneous treatment effects, remember this is like the individual level treatment effect, they're often like very not well pinned down by data. In particular, the scale of how heterogeneous the effects are seem to be very, very difficult to actually learn in a reasonable way. And I'd be interested in hearing alternatives to being Bayesian to do it, but from my perspective, there's not much recourse, but to try to adopt Bayesian thinking into figuring out what to do in this kinds of situations. So, and this is going to be simulation, but it's a simulation from a based on a real data set. This is like based on the effect of smoking on how one's health, the self-perceived health. So the idea is you smoke, smoking people tend to be unhealthy, and therefore they are likely to rate their health as being somewhat lower. Okay, so that part's not so important aside from having the motivation and kind of knowing where the magnitudes of these effects come from. But I basically took this and I generated some simulation settings, and then I fit a bunch of methods. And then the important point is not so much the specifics of what these methods are. So there's a Bayesian causal forest. There's a causal forest, which is this method by Susan Athey and Stefan Vager. There's a ridge regression thing that I just sort of threw in. And then there's this thing called the R-learner. The important point isn't so much what these things are as it's how different they are, in the sense that you fit 4 reasonable things. And I do think all of these things are reasonable things to do. And you get just vastly different answers. You're doing something kind of sensible, and somehow you're landing on very different statements about how different the effect is from person to person. So these are just histograms of the overall estimates. And then, of course, you can also just compare them to the truth, because we know the truth. And you just sort of plot what is the estimate against what is the truth. And you see a shocking amount of noise. You see, like in the case of a causal forest, for example, you get the estimate is almost completely uncorrelated from the actual effect. In the case of the R-learner, it happens in this case that it just zapped the effect entirely. So also kind of uncorrelated. The two other approaches are the Bayesian causal forest and the ridge regression, which I'm not intending to say that these are superior methods at this point. I've already sort of argued for using Bayesian methods at frequentist terms, but they're very, you're really not estimating these things with very much precision. And it's sort of like not so, it's not really clear what you should do from this position. Another thing that you'll find if you play around with these things is that even in these sort of simulations, often what you find is that shrinkage is important even if the sample size is sort of seemingly quite large. So by seemingly large in this case, I mean like if you have 20,000 observations and you have 10 covariates, right? I think you should feel like, okay, I'm in a pretty reasonable situation here. And often you end up in seeing, if you play around with these things, some very strange things. So one of the strange things that we found, so this is with my student Angela, and tell her like, okay, go simulate some data, make one of the truths a BART and make one of the truths a linear structural equation model. So like this particular problem. And then I want you to go then fit the BART and linear structural equation model to the BART ground truth and the linear structural equation model ground truth. And what you should see is, well, of course, if the BART model is correct, then it's going to do better. And if the linear structural equation model is correct, then it should do better. But it didn't do better. And how that this you see this sort of thing and you're sort of immediately thinking like, well, this there must be some mistake, right? Like how could you have the ground truth be a linear regression? You don't have a very big p, and you have a lot of observations. Isn't there some theorem that tells you that this can't happen or something, right? Like how are you losing to a nonparametric method? And then we ultimately landed on was that these things are just so not well pinned down that it's more important that you shrink appropriately than that you actually get the model correctly. So this is another way of saying these things are not particularly well pinned down, is it's a regime in which shrinkage matters more than getting the model getting the model correct. And this isn't like so much a BART thing as it's important to regularize things appropriately. And then we had this conjecture and we sort of confirmed it by looking at this other kind of linear model that induced the same effect, but a little bit more extreme. So this is also a linear structural equation model, but fit in using a different technique called an R learner and able to exaggerate the effect by making it more extreme. Okay, so what are the options? I mean, so one is to give up, and that's not necessarily, I mean, I think it's good to not be too idealistic about what problems are solvable and what problems are not solvable. But I mean, for certain important problems, maybe you don't want to give up. Another way you can do is sometimes maybe reframe the problem. So maybe I think that estimating individual effects is too difficult. Maybe I'll switch to something that is somehow in between an individual effect and the average effect. So the average effect is very coarse, right? It's the average effect over everybody. I have the individual effect, which is like sort of U-specific, but maybe I can define subpopulations, maybe possibly in an adaptive way, and maybe I can switch the problem framing such that I get something reasonable. So those are both reasonable, and I'm going to maybe do the least reasonable thing, which is like to try to be Bayesian and think really hard about how I can try to make my prior as trustworthy as possible. Try to use Bayes to sort of break the tie among these different options. What I want to be able to do is I want to say like, well, what I want to be able to have a prior that kind of comes in and like helps me resolve these, because some of these, I mean, in this particular case, if you look at what the causal forest is doing and keep in mind how the data was generated, the causal forest is so sort of extreme that it's actually estimating a positive effect of smoking on perceived health for a subset of the population, which seems implausible. So maybe I'd like to rule out those kinds of implausible events, restrict my my model space to something like a little bit more reasonable. So what should a good prior on a heterogeneous treatment effect function actually look like? And if you think just in terms of application, you know, if you're going to design this thing, now I list 3 properties that I would like this thing to have, but well, none of this is true in general, right? This is all statements about the types of problems that I, you know, being someone who likes to work with health data or expenditure data, what do I expect to see when I'm like sitting down and looking at a problem? Well, generally what I expect is to have small treatment effects. You know, you're very lucky if your treatment effects are very, very large. And by small, I mean small relative to the overall error. So the variance of the intrinsic variability of y is typically going to be larger than the treatment effect. It's also typically going to be, you know, smaller. You know, the treatment effect is going to be smaller than the prognostic effect of the covariates. So the covariates are usually soaking up more than the treatment. I also usually expect the treatments to be relatively homogeneous. So I expect the variability in tau x to be reasonably small. And I expect the treatment to be, or I expect the mean, this is a little bit hard to frame, but I expect there to be some correlation of treatment choice or how effective the treatment is with whether I receive the treatment in the first place or not. Or basically, I kind of expect there to be a relationship between the propensity to receive the treatment and the effect that I actually get. So I would like a prior that kind of captures as many of these things as I can. So one way to do this is to sit down and like, well, how do I do that? Right? I'll just write my treatment effect function like this. It'll be some overall effect that will let me capture the overall average, which I expect to be small. And a second piece that captures overall heterogeneity. So I have a secondary tau star function that will capture overall heterogeneity. And by saying I want this thing to be relatively homogeneous, more or less what I'm kind of saying is I want this secondary piece should probably be of smaller magnitude than the first piece. So the contributions from this term should be relatively small relative to the main effect. Okay. Now, I mean, you might hope, and I guess in a lot of these things, and you know, younger version of me, I think often fell into this trap of expecting, you know, Bayesian nonparametric priors to do more than you kind of they can sometimes give you a false sense of security in terms of like you expect them to be able to adapt to things that they maybe are not so well. I mean, the way that I have to think about these things is, your Bayesian nonparametric parsers like really says they're very informative about very many aspects of the data that if you're not almost hand wiring it to not be informative about things, the default expectation is that it can be quite informative. One of the things with, say, a default BART prior is that it is, I would argue, like somewhat relatively informative about the maximal, the maximum of the process. So, for example, and you care about the max in the sense that maybe you care, maybe that's linked to how heterogeneous the function is, right? The magnitude of this tau star x. That's encoded pretty strongly in, say, a default BART prior. So it bears some thinking for how you kind of deal with these things. So one potential option, and this was proposed by my colleague Jared Murray at UT Austin, along with Carlos Carvalho and Richard Hahn, is a Bayesian causal forest. This is one particular take on it. This isn't the specific thing that they wrote down, although what they wrote down is also very reasonable. Agnostic effect, for reasons I won't get into, it is genuinely a good idea to replace a regression on A with a residual from the propensity score, hit that with the treatment effect function, and then you just sort of put BART priors on everything, and you hit the go button, and everything sort of seems to work out reasonably well. There's lots of room for improvement, and I think that one of the lessons that we've been learning over the years in kind of doing this is there's all sorts of parameters. You really start scrutinizing these BART prior parameters very, very carefully because you realize exactly what they're encoding about your prior beliefs. Like choosing the scale of the BART prior, for example, is very, very important. You're almost like hand picking the degree of heterogeneity that you're going to be able to find. And I don't think we have great tools for figuring out a good way to elicit prior beliefs about degrees of heterogeneity. You can kind of do things reasonable, ballpark where for example, the overall effect should be based on looking at prior literature. So if I'm like doing a drug study or something, I can look at similar drugs and get a sense of like where the effect is. But it's not so easy to do that for eliciting the degree of heterogeneity. Like how do you elicit? Maybe this is like the way to frame it for the current audience. If I wanted to elicit a covariance function for a Gaussian process, if I want to do so somehow in an informative way, how do I do that? Like what is the right questions I should be asking someone if I genuinely need to be informative about it? So I'd be interested if anyone has any ideas about that. Right now, what people tend to do is use a combination of default priors and vibes and simulations and sensitivity analysis to try to build up some sort of working knowledge of what seems to work in practice. So even though I don't necessarily have a great sense for how to elicit these priors, I can gain some confidence by, say, doing extensive simulation studies over a variety of different data generating mechanisms and just sort of seeing what happens and seeing where I get good behavior, and then crossing my fingers from there. Another thing that people will also tend to do in this case is undershoot on the heterogeneity. So the heterogeneity is being dictated by this term. If I underestimate the heterogeneity, that some people interpret that as being conservative, in the sense that when I'm wrong because I undershot rather than I overshot, which there's a preference in a lot of fields for erring on the side of saying things don't exist rather than that they do exist. A couple of other things. I really think that so it made the claim that doing these things properly is important, and there's a lot of ways to shoot yourself in the foot doing these things, and I do think like some of these lessons I hope carry over to all areas where people apply Bayesian nonparametrics. But Bayesian thinking can be quite illuminating for some strategies that clearly will not work. So one thing that clearly will not work is stratifying by the treatment, treatment effect and just fitting two regressions. So if I had just say, take the treated, fit a regression to them, take the control, fit a regression to them, and then just take the difference. If you just analyze what the prior is saying, it's clear this is like a ridiculous thing to do. Why is it a ridiculous thing to do? Well, you end up with a treatment effect that is larger than the prognostic effects, which is something that you just sort of know a priori is very, very unlikely to be true. Additionally, you generally will have the heterogeneity scaling with the complexity of the functions of the means for the two different groups. Like, so just immediately it tells you for free that this thing is not a good idea to do. And you can see in practice that it really does make a big difference to get these things right. So I have a competitor to the thing. I'm just sort of a straw man to beat up. We have two batches of data. So there's treated in blue and controlled in black. There's a constant treatment effect and then just a nonlinear relationship across X. So I'm interested basically in the gap between the two curves. The gap between the two curves happens to be constant, although the models don't necessarily know that. If you do stratification, you get this horribly wiggly estimator, whereas if you do the good version, you get something pretty close to ideal. So parameterization really matters, and being non-informative about things without being very, very very important to have a good sense of what prior information your models are encoding, because, and I say this like, these examples are based on things that I've seen people doing, so it's not as though I'm being completely manufacturing, that these mistakes actually occur. Another thing that you end up finding is that there's this idea of having an ignorable prior. An ignorable prior is one where you basically have a model. So they were way back at the beginning. Remember, there's the prognostic effect of the covariates, that's mu. There's tau, the treatment effect. And then there's the propensity score. That's what E is. That's the probability that you receive the treatment. And there's a big motivation to have that piece be a priori independent. And people like doing this. They like doing it because it makes it so you don't have to model the propensity score. So there's a big modeling win. I mean, it's not that big of a deal to model the propensity score, but people, why model it if you don't need to? And there's not any obvious reason that you're really shooting yourself in the foot by doing that. This leads to what are called outcome regression models, just kind of in general. I'm going to only use the outcome. I'm not going to use the propensity score at all for doing inference. These are bad, and they're bad in the sense that they can encode very, very bad prior information in the data. So this is from a paper I had in 2023. This is concerning the induced prior in a particular parameter called the amount of selection bias. So if it's big, it means that there's a lot of confounding in some sense. If it's zero, in some sense, it means there's not so much confounding. A priori, you should probably believe that there's, if you're doing causal inference, if you didn't believe there was selection bias, you wouldn't be using causal inference techniques. You would just be doing whatever you want because it's not a problem. But you sort of see if you use an ignorable prior, as the dimensionality of the problem increases, you inadvertently end up concentrating the prior on this amount of selection bias to zero. This paper looks at a couple of different ways in which this phenomena occurs. I mean, it's known from some time before this paper as well. But yeah, it's very, very important to not just have good sense of what the induced prior is on heterogeneity and so forth, but also on the degree of selection bias, and not be tempted by things like specifying ignorable priors in general. I'll talk a little bit about the winners, because this is one that This is probably the most irresponsible part of the talk, but it's in a positive audience, I think, for the message. So I'll try and go with it and see what happens. So I mean, this motivation for this comes from a problem of policy estimation. So I mentioned like a long time ago, one of the options to the infeasibility of estimating HTEs is to switch the problem a little bit. And one of the ways you can switch it is to focus on subgroup estimation. One of the reasons you might want to do this is for, say, policy, right? So maybe I want to estimate an optimal policy that assigns people to different, you either get the treatment or you don't get the treatment based on some features, and I might be interested in estimating treatment effects within each of the nodes. There's lots of reasons to do this, not just for the infeasibility issues, but also just interpretability. It's a lot easier to interpret things like little trees rather than whole big heterogeneous treatment effect function. Formal framework's not too important. Basically, you just have a utility function on the set of policies, and you use Bayes' rule. You just get the Bayes estimator. But that part's not so important. But now you have this, like, so let's say you're sitting there, you estimate some subgroups, you get your policy, and you want to do estimation of the treatment effect within each of these subgroups. Now, how should you proceed? And the Bayesian and frequentist methods diverge immediately from here, right? For frequentists, this is post-selection inference, right? So the standard line is like, well, either you should have cut your data in half, or some other percent, get the policy and then save the other half and use that for inference. And you should probably use do some data splitting. But that's not what Bayes says, right? What does Bayes say, right? You just use the posterior. You don't have to do any sorts of corrections for anything. If you believe your prior anyway, then you should just go ahead and just use the posterior. And so, well, what do you do, right? This is something that I genuinely struggle with, because my impulse is always, if something is wrong from a frequentist perspective, that it's worth digging into, and not just, but there's always the temptation, right? You want to go as Bayes as you can. So right, the frequentist is saying you can't do that. The coverage is going to be wrong. There's no reason the Bayes should cover, and all this stuff. And the Bayesian over here is saying, oh, you guys should believe your prior. There has to be some ground truths where this actually does work. Because coverage has to be maintained over if you do something horribly data adaptive, you're doing a Bayesian procedure. You're getting coverage conditional on theta. And if you average that over the prior, it has to, if I have 95% conditional coverage, then I have it marginally over the prior as well. So there have to be some thetas for which this is actually a genuine thing I can do. And if you believe your prior, then you should just be okay with this. And the upshot from doing this is you get to keep all the data. So you don't have to do any data splitting, and you just use the whole thing, and you just trust Bayes. And I mean, people do this. There's this nice paper that Carlos and Jared and Spencer Woody wrote that makes this point. They do all kinds of data dredging things. So they introduce this posterior summarization framework. They summarize Bayesian nonparametric models, and they give the line, right, these summaries naturally come with valid Bayesian uncertainty estimates. And since we only use the data once to go from the prior to the posterior, all of this is valid, right? It's all valid uncertainty, even if you arbitrarily, iteratively refine all of the summaries that you get. So, okay, but you can do this, and they certainly have been successful in getting these things into the applied journals. And when I try it, it seems to work. So it's sort of funny that, I do some loose experiments with it. And so this is all sort of half-baked, as ongoing work. But I mean, I'm finding it like somewhat difficult to actually get the bad behavior to come out that I do it. But I'll say that one of the very, very important things, so there's this ignoring thing. It's important that the prior is reasonable, because if you write down unreasonable priors, things really don't work. So in particular, this was a linear model. So the ground truth of the linear model, and you could either do full Bayes, use all the data, and you use some mildly informative priors. So they were priors, but they're like quite, not like overfit to the data, but like somewhat informative. Versus using methods that are kind of guaranteed to work because they're based on data splitting. So all the other methods based on data splitting, and they all have best coverage was the Bayes that used all the data, and it was much narrower because it used all the data. If you use flat priors, it doesn't work. And I don't have the figure. I lost the figure. I apologize. Very sad putting these slides together, and I couldn't find it. But you just believe me, if you use flat priors, it doesn't work. And it kind of makes sense, right? Because a flat prior, if the prior was really flat, you'd basically, well, you sort of, the model is saying that the betas are all so big that the problem is trivial anyway. So anyway, yeah, that's just all I wanted to talk about. So the summary, right, good nuisance function estimators should be good even for frequentists in a lot of settings, for a lot of things they use. I think that Bayes gives us a sensible intuition for what HTEs should look like, and some kind of take on post-selection inference.
The last paper that I somewhat disagreed with your statement about Bayes versus the last one. You were saying that there's a assumption that Bayes is valid, that you can correction, as long as you specify particle. I feel like in this case, you don't need data splitting, not because of the prior, but because you only use the right conditional perspective. Rather than reusing cycle like twice that cause the problem. Now, of course, just because you use likelihood twice doesn't mean that you don't have to be careful with regularization and for things. So the prior is important, but it doesn't seem to be a critical aspect of Bayes. I feel like you could do similar things with some tricks with likelihood, like partial likelihood or something like that, which does some splitting on the likelihood without some prior. It's still pretty okay with that.
So I may have a slight difficulty parsing the exact question. I think that the issue is the claim that something to do with that I'm saying that about the use of the prior. It is true in this case, like if I'm staying in the usual framework of prior plus likelihood goes to outcome, the prior is important for like this data dredging stuff. If you use a bad prior, it will not, like, that thing will not work, right? Like if you use, for example, in this particular situation, I wrote down a specific prior here. I happen to give 95, 97% coverage. Flat prior does not work, right? So if you use a flat prior, it will not work. Now, I'm sure there are other ways, right? Flat prior, I think, the reason I think that this is like, it's reasonable, you shouldn't expect it to work, is because the prior doesn't represent anything like what I actually think is going on. I'm sure there's other ways around it. Like you could get some, you could, resolve that issue in some other way rather than through the use of flat priors. Maybe you have some kind of database prior that kind of comes in that also could act to stabilize it. I don't know if that's sort of what you're getting at.
So I'm just saying that prior, if you don't specify the prior, of course you can do that. But you do that not because you double dip the data. You do that because you're given proper regularization or proper penalty. It's not because you used a selection bias, which was the problem of double dipping, is the same data twice, you learning and then doing inference. That's double. But here you use a flat prior and do that out of that. It's not once, but you may still be very careful with the prior. So that's what I was saying.
Well, so think about it in the case, like, let's say that the flat prior was correct in the sense that the coefficients were all really big. Then it actually would work, like, it would work well in that setting. So like the claim is, if the prior is, like, if the truth looks like a sample from the prior, you can do these things without worry. That's the claim. What's happening, right, is that there's this winner's curse phenomenon. You'll tend to, if you don't regularize, what will happen is you'll end up the groups that you select, you'll end up overestimating the effect. And the role of the prior is kind of like to bring them back to something reasonable. So you kind of get these two forces. There's selection that's pushing the effects to be large, and the prior that's kind of shrinking them back into be where they should be.
Yes.
Yep.
Tom, UCLA. In the literature on causal inference, there are a number of methods that view the potential outcomes as more like attributes of the unit rather than.
I'm not very loud.
Oh, sorry. Yeah,
I can. Yeah.
but
you can use.
the question in causal inference literature, there are a lot of methods that will be, inference will be anchored by thinking of the potential outcomes as attributes of the unit, and then maybe simulating like a permutation distribution or randomization distribution. And it seems like most of what you've done is more of a model-based inference approach. I was just wondering if you delved into that in your work. Have you explored differences in that later stage of inference, and how does that impact any of the approaches that you take?
Yeah, I think that so I keep a respectful distance from the randomization perspective. So that right, the ideas you sort of almost think of the units as being fixed, in that all the randomness is coming from the randomization mechanism. Yeah, I think that somehow the Bayesian. I mean, I don't want to speak for. I mean, someone could immediately contradict me on this, but my sense is that it's the Bayesian approach is sort of like more naturally leads to this kind of outcome type, like modeling all the like viewing everything as being random and just modeling it all as random. Although, I mean, historically, right, I guess, you know, a lot of these ideas are starting with, you know, well, Don Rubin popularized, let's say, a lot of this stuff, and he was certainly very deep in both of these approaches. A nice thing with the randomization mechanism, you know, randomization approaches is that they, you know, you're if you believe the assumptions, if you believe what is required to go along with it, you know, it's there's less worry about these sort of model to specification issues, right? You don't sort of worry quite as much about it.
Now, running the questions. Sorry.
So in your model, you're assuming normality is something to error.
Oh yeah. For all of the examples, and I mean all of these, you know, I'm primarily focused on simulation just because that's, you know, I know the answer. Like I can make the points that I want to make. And yes, that the very beginning, yes, there's normality in there. Of course, yeah, you can make the normality go away in various ways. Yeah.
Basically, probability assumption lends itself to moment-based estimation, because the assumption is basically saying that something is, and potential outcomes then depend on the treatment given behavior. So you can, without making any assumptions about the error, set up the
Mm-hmm.
and so I have the paper in GRSP that shows you how you can estimate the ATE using splines and so forth. Just working with my data.
Yeah.
Can you give it a short answer, then we can go to the last question?
Yeah. Yeah. So, yeah, definitely. There's many, presumably many ways to get around having to. And I agree. Like dropping it, the pure moment-based approach. That's especially pure Bayesian, pure moment-based approach, that sounds fantastic to me for estimating things. Yeah.
There were a lot of questions. It's one question there. Yeah, sure. I have a question about this idea of target selection.
Mhm.
Previous scientists correlated with prognostic.
Mhm.
And so to me, this seems very similar to like this not a random problem. You know, the typical approach is to, I mean,
So yeah, it's not quite missing. So it's not missing. It's very adjacent to it, but it's not missing not at random because you do have all the you have measured everything, right? That's not what the problem is. That for the targeted selection sorts of things. The problem is that the models are not so naturally inclined to point in the direction of the propensity score unless you force them to. It's a little bit hard to say exactly what I mean by that, but like, you know, if you just write down a model, like a BART model or a Gaussian model, whatever, and you say, let's say I take a random function of some covariates, say it's a Gaussian process, and you have the propensity score over here. So it's some function, there's some other function that's drawn randomly. The prior probability that those two things are going to be correlated is basically 0 in high dimensions, unless you build it into the model. Just if you pick any function and you take a random Gaussian process, that Gaussian process is not going to be correlated with it. Like they're gonna, the inner product, they're just not going to be correlated by default. I don't know if that is related to the point, but yeah, it's not quite, it has a missing not at random feel because it's almost as though, even though you controlled for everything, you didn't have the propensity. It's almost as though you didn't control for the propensity score, even though you controlled for all its individual components. It's almost like somehow you still didn't quite control for. Yeah, it's weird. I'm happy to talk after about this. Yeah.
sorry, I think that close to the question.